So, this is last lecture of risk-based engineering, and the title is special areas, and overall umbrella is risk conscious operation management of our complex engineering system, and this is based on my own model, that how much or what should go into risk conscious operation management. So, the risk based engineering is a very wide subject. In the book there are 15 chapters, everything cannot be brought in one week. So, something I have given in detail which you saw that are last 4 lectures, and some of the aspects now I am discussing which I could not cover, which were part of risk based engineering book. And first topic was probabilistic fracture risk assessment. Okay. So, this was one of the chapter of risk based engineering, and I thought let me touch upon this thing. Details you will find in the book. I will here touch upon some Paris law and crack propagation, crack initiation, those concepts, but then let us understand the importance of this area. In engineering industry, 80% of the failures they happen because of cyclic loading, and cyclic loading induces fatigue, and this fatigue fails the component well before their either design life, if the fatigue was not factored into the design, and it is one of the, so 80% of the failure can be attributed to the fatigue failure. Okay. Second important topic is human reliability modeling. So, I am touching upon here just for the sake of continuity, otherwise in risk conscious operation management this is an independent lecture, one of the week it will take, and there cannot be any shortcut. I have to devote time on this, and similarly prognostics and health management, which is part of risk based engineering, but it has not been covered as a separate chapter, and here I will be touching upon this aspect also. And root cause analysis we have been discussing left and right. Prognostics and health management, earlier it used to be breakdown maintenance, then it came preventive maintenance, that is having a fixed schedule, and then we had predictive maintenance, and where condition monitoring was also part of it. So, the state of the art up to condition monitoring is very sound, but when we talk about prognostics and health management, this topic is still in the R&D domain, and in some high-end industry where they have very strong collaboration with the academia, researchers and all that. PHM has found its way in terms of residual life estimation, let us say battery, lithium ion battery, lot of research is going on. Then bearing remaining useful life estimation, lot of work is going on. So, some fracture risk assessment there also, but the problem with the fracture risk assessment is it has got lot of uncertainties. How the fracture location will behave, which direction orientation will go, they are uncertain areas. So, but then this is where the focuses are there on prognostics and health management. One is remaining useful life, other one is overall maintenance management. Before the failure occurs, a corrective action can be taken, and for operation ecosystem this will be a very valuable tool, because at present there is a condition monitoring on say bearings of the mega pumps. Now, the temperature will go up, vibration level will increase, and that will give an indication in the control room that situation is deteriorating. So, here we have advantage in the sense that we will not go to the failure condition. Okay. But at the same time, if you have taken a decision too premature, that means we lost the life, we had to shut down the plant and it affected our productivity. But if we delayed it or we became little on chance, then we lost it might result into fire, that is unsafe events. So, the idea of prognostics where the remaining useful life is predicted along with the uncertainty bounds is a very attractive way. Of course, the uncertainty bound should be crisp, it should not be too large and all, it becomes meaningless. So, the point is PHM is still in the R&D domain in limited elite labs and certain plants or certain advanced systems it has found its application, but one thing is it is accepted that PHM is a thing which has to be persuaded. So, if you look at the probabilistic fracture mechanic, we have three major reasons: crack initiation, crack propagation and catastrophic failure. Okay. Catastrophic failure means there is a critical crack size is crossed, and now the component can fail anytime, it will not give time actually. Okay. And it is mostly applicable to structural systems, like you can say piping, tank or pressurized, especially pressurized systems actually. And probabilistic actually is required here. Why? Because the modeling for crack is a very area where every aspect of crack initiation to crack propagation to catastrophic failure is less with uncertainty. Okay. And even though it is also advantage with the crack analysis is we can simulate experiments on universal, will show on the next slide. It is easier. So, that advantage is there, experimental facilities can be built and all, but then the field uncertainties are totally different. One time impact, we will not go into detail, then corrosive conditions, internal corrosion, external corrosion. So, attack is happening from both the sides. One is the internal defect which remains latent, then external corrosion condition. So, our factor of safety is coming down or our uncertainty is increasing. So, that is the situation, and this is where real science has to develop. Lot of research papers are there and all, like in aviation it seems because all the cracks are not dangerous. Sometimes the cracks are there and they remain latent and they never become critical, but some cracks they might become critical after certain. So, those kind of things only expert can talk about it, but when you built into the system there are no experts available. So, some sensor module, I will come to that, has to be developed, then data has to be processed, and most of the time it requires intelligent processing and things like that. So, okay. So, and there was SN curve, stress and number of cycles curve, then finally fracture mechanic came, then now it is I am focusing myself to probabilistic PSN curve, probability, stress and number of cycles. So, you can see here, so this gives little more complete picture, and PSN approach is becoming very popular in fracture risk assessment. Fracture risk assessment means every crack has got some penalties associated with this. So, that is why even if it is a plant shutdown, it is called reliability risk. You are losing something on reliability. If it is an accident, it is a purely a risk thing where fatalities are the consequences. Okay. So, and the traditional approach to handle the on surface volumetric cracks detection was in service inspection. That means there is a percentage criteria and those locations will be inspected, and NDT methods are applied there, and try to see whether there is any, especially around the weld. Weld zones are really sensitive because heat affected zone around the weld, they sometimes require special attention because any cracks there, because neither it is a best material property nor it is a weld material property, it is in between. So, this requires really a thorough assessment for qualification. So, what is happening is whenever any thermal hydraulic system or mechanical system is operating, we have seen of stress varying in a cyclic manner. Okay. This is idealization. Normally diagram will not be leaked, and then maximum stress, all those factors are determined from here, maximum stress to minimum stress, then spread, then amplitude and all those things, and they provide a matrix for us for risk propagation and all that. And here we have a very universal statement that is called Paris law, which is a mathematical formulation of crack propagation procedure. So, dA is the length of the crack. Normally in science we have elliptical as the size we take. If crack is not there, it is assumed. So, then the story starts from not crack initiation, but crack propagation. Okay. And then number of cycle required, C and M, they are basically material constant, and then K represent the change, delta K, that is change in stress intensity factor. So, how much intensity is changing, and this becomes, so that means dA upon dN is proportional to stress intensity factor, and that is become the governing equation for most of the equation. And how we simulate these experiments, it is on the universal testing machine where cyclic loads are given, and finally material behavior. Sometimes the cracks are deliberately inserted or created into the specimen, and then they are studied, sometimes volumetric cracks, sometimes surface crack. So, it has been seen that even surface cracks which are minor, they propagate into volumetric cracks, and it becomes catastrophic. And that is why in service inspection, even if any cracks are seen on the surface, it is basically handled by polishing or something, so that stress concentration is not created, or some additional material deposition over there through welding or any other technique. So, this is all about, and then probability is again, as I told you, this approach remained in deterministic domain, and now people have realized, like we talked about deterministic approach, wherein uncertainty best estimate probabilistic upper bound and lower bound came here also. So, here we complete the scene. If you want to read this subject, because time was the constraint, you can open any book and see it for how probabilistic stress, probability, stress and number of cycles, they are correlated. In my book I have dedicated, that is risk based engineering, I have dedicated one independent chapter on this, and many materials outside. Now, second important topic was human reliability. Human reliability, I am showing only one slide here, because in detail we shall be handling this as an independent lecture. So, human reliability and common cause failure, they trouble an analyst. Why? Because one thing has been understood, that uncertainty associated with the human reliability statement or human reliability data and common cause failure data is higher compared to our hardware component failure. Why? Because human is a complex system to model, and common cause failure, even though there are implicit consideration of the causes which can result into common cause failure, in plant operation or design, provisions are made, like 3 redundant pump. If they are located in one location, they have physical separation. Why? Because a single common cause, let us say fire or other things, or even flood, they should not affect the other system. If it is a float prone, then barriers are also created. Fire prone, that means by fire walls of that much fire load capacity are created between redundant system, so that common cause failure should not. So, common cause failure is a well known phenomena in industry, but when you do the risk analysis, you will find that this comes on top, because independent failure, they do not contribute much, because there is a redundancy. If one component fails, second is there, third, fourth, there is a difference in depth is there. Similarly, human reliability. human reliability also, because of large uncertainty created, and sometimes we put two persons for the same operate, but everywhere it can, sometimes when we are dealing in cognitive analysis or cognitive level where stresses are very high, even probably it will be human reliability becomes more important in accident scenario. Why? Because the human was to use his cognitive capability to the extent possible, but the stresses that are built during accident condition, it brings down the cognitive capability of human. So the same scenario where cognitive capability was required, the cognitive capabilities are less because the stress is a common denominator. Okay. Now, as part of risk based engineering and new human reliability model, so in the research that that I performed as part of risk based engineering, I found that consciousness, there is no role of consciousness. It is an indirect symptomatic consideration in terms of focus and all that, but consciousness was not considered. But consciousness is fundamental to human existence. So then there is an approach. So it is called CQB approach. That means the three C's are there: consciousness, cognition, and conscience. Why conscience? Because now we are dealing in an arena of security also. So conscience is also required, where we have to account for human integrity, moral, ethics, and certain behavior which are intended. They are not random, because so far in our PRA we have been dealing with random phenomena, but here it is deliberate phenomena, motivated phenomena. So we have to handle this, and then the physical and psychological stresses. As I mentioned, during accident condition, human capability comes down. So the factor which drive the whole human reliability methodology in CQB is stress ratio, not the time available. Stress ratio means what is the inherent stress handling capacity built into the system, and what is the stresses that the operator might explain. So that gives stress ratio, and this required a lot of experimentation to be done, but finally it made the human reliability model more robust. So one is 3 C's, second is stress handling, so performance shaping factors, they were built based on stress ratio, then any other attributes like time, context and all, because everything together is forms the stress. The approach provided framework for human root cause analysis. Generally it is seen that in open domain, the human, once you reach the human level, it is considered as a root cause analysis. No, human root cause analysis is one thing and reaching human root is another thing, because coming down to the level of mistakes, error, mistakes, sleep, and all those 4 or 5 factors, and ending the exercise there. It is not why the human did the mistake, whether physiological, psychological reason. So for that, in simple word, we have to go a human model. So in CQB method, there was a human model wherein human root cause analysis was a natural way of achieving it. And for consciousness, conscience takes care of conscience element enable modeling of security. It should be conscience, not consciousness. Conscious element enable modeling of security aspect through the factor ethics, integration and all that. So CQB method major objective is to reduce the uncertainty associated with not only estimation, understanding of uncertainties is also very important. There is a separate module on human reliability analysis in this risk conscious operation management for complex engineering system. So I will go to the next topic, that is system approach to prognostics and health management. This is a new paradigm or a additional paradigm in the area of prognostics. In prognostics, generally we talk about a component, structure or a system. But then if we look at the mega plants, in which it is not easy to find a optimized way where we should go for prognostics, because prognostics is a very expensive, resource consuming exercise, R&D consuming exercise, It's not that we'll put sensor everywhere. Only few selected locations which require, like it could be life limiting, or it could result directly into unsafe situation, or it is a part of life extension program. So that is where we can put prognostics and health management, because intelligent processing form part of prognostics and health management, like it is machine learning, artificial neural network, support vector machine, they call, and the objective is to assess the remaining useful life and support the decisions. Once I know where I am, how much time is available with me, I can take decision in real time in plant control room scenario. Now, so I am listing out various reasons, also expensive exercise, so the need for identifying the priority. But why I require systems approach? Because when I have a PRA model of the plant, I can prioritize the safety requirement. It could be plant policy, it could be components, system structures and component, and then I can determine very easily where I should, and then if I am able to see benefit in terms of reliability, availability and risk also altogether, then definitely I should go for PHM. Further, the priority will be given by life limiting components of the plant. Especially this is very important when the organizations approach a regulatory body for life extension of the plant, then regulators will ask, these are the core limiting components, life limiting components of the plant. Tell us what you are doing. So there could be a easiest way. We are going to implement a prognostic approach wherein we will get the information about the remaining useful life of the component, and it sounds convincing. It is expected that the system approach to PHM will result in maximization of plant reliability, not only safety but reliability also. So let us see how we do it. Well, we have SSC from nuclear plant where we have identified based on the thousands or tens of thousands of components. We have identified some number of SSCs. Let's say bearing for something, or for some piping, or some support, and then so we have put a sensor. The sensor could be vibration sensor, temperature sensor, stress sensor, impact sensor. So information is coming to online sensor for tracking precursor. So we have to identify, first job in implementing PHM is identify the precursor parameters. It could be 1, it could be 2, depending on the situation that we are handling. So, and then we should have a prognostics algorithm. That means always linear case will be there. So this is where the intelligent approach is required, and the system like artificial intelligence or machine learning approach, where system has to be trained based on either the past cases or experimental data, how the failure or degradation will proceed, and it will touch a threshold value. There is a threshold value. So before that threshold value, we have to have, because it is a prognostics and health management, so we have to take some corrective action, and then finally uncertainty, whatever estimate is there, uncertainty prediction we have to give upper bound of the band. So this is a distribution. I have shown it by normal distribution here, and we will get remaining useful life statement with uncertainty bound, and this form part of the risk based engineering applications. Okay, so this is just a slide where systematically when we are setting a problem and we are trying to work out on problems, what we have is integrated risk as a risk model of the plant, like PRA model of the plant. Identification of prioritizing, so that will lead to identification, and then it will lead to precursor signature monitoring, which signature to be monitored, and input to this thing will be from deterministic, probabilistic, precursor event analysis and uncertainty characterization, which will get plugged into the prognostic framework. And the prognostic framework in turn, so it operates in a closed loop till it predicts the remaining useful life, available time and safety margin, planning and action, prediction of life and reliability, updated dynamics, because the loading also on the plant they keeps varying. So, we have to factor in the additional loading impact also in the plant, feedback and performance tracking. So, here and we will have as a part of this we can say prognostic framework, remaining useful life will get, and then it will give another feedback which operate in a closed loop. So, what is required? We should have a dynamic model of the plant, like dynamic PRA, or even if a static PRA also will do for major part for identification, and precursor analysis also will be required. So, and then finally, this particular chart will be more applicable when we want to develop a prognostic algorithm, a system for something, and we can use this chart in operating plant. Now, proposed PHM for nuclear plant, something we have adopted from there in the previous thing. So, we have a nuclear plant. This is one paper I have published through PHM Society. You can see in the open domain, it is available, and it is I think in the 2012 or 11 it is there, that is role of prognostics in risk based engineering. Okay. So, nuclear plant we have design information, corrective action program is there, monitoring. So, they operate in closed loop. So, design and performance requirement, online data acquisition, then monitoring, surveillance and all, and corrective action program. So, this is how plant operates. Now, if you have to implement PHM, so now we have to install PHM sensor, and the data has to be obtained, online data acquisition from this. So, online data and PHM sensor, they are there. Okay. And then we go to prognostics algorithm. Okay. And there we combine with other data also, and through Bayesian updating or ANN for super, and finally the optimization prognostics and real time life reliability prediction, other remaining useful life something. And then here we have FMACA or PRA model also, which can plug into here for prognostics algorithm. And this is how for a nuclear plant we can do it. But I do not think it will make any difference if even if you implement it can this framework can easily be adopted for any other plant also. But yeah, PRA model must be available because that is very critical for identification and prioritization of the scope of prognostics. So, in this lecture we have seen the special topics, the prognostics and health management, fatigue and crack risk assessment, human reliability in just one slide because we have a separate chapter on this, and role of deterministic and probabilistic we have discussed. So, if I give the overview of the week, it is like introduction, one lecture, then risk-based framework was discussed in the second lecture, deterministic and probabilistic, two lectures, separate lectures were dedicated on this, and then the special area. And with this, we complete the third module or third week, risk-based engineering, which provide the fundamental framework for risk-conscious operations management. These are the papers which are available in open domain. Okay. And there are many others also, and so many sources, international sources, International Atomic Energy Agency, Nuclear Energy Agency, and and then with this week 3 on risk based engineering ends here. Thank you.